I'm going to stand here because I don't want to hide behind this thing. Otherwise, I feel awkward. So good morning, everyone. I'm very happy to be here because before I went to my first conference, this is the first conference I have ever heard about from Martin Splitt. He was saying, this is the most awesome conference ever. So I'm very, very happy to be here. Thank you for the invitation. Yeah, as I was already introduced, my name is Madlaina. I'm actually a game designer, but I am now more focused on full stack development. And my aim is to make 3D content accessible for everybody. So obviously, I really love games, and I extremely appreciate what has been happening here before from RuhrJS, so I would want to give them a shout out again. They're really awesome, and I can't wait for the party. Yeah, I also really like traveling and being creative, and I have a lot of other hobbies, so let's talk afterwards. 3D and the web, why is that important? So, for example, we now are in the stage where webVR is really booming, and a lot of people want to go down that road and experience how they can provide their information in 3D and what this actually means. So, for example, you can have architectural visualization. You can create games on the web in a very easy way that are fully immersive and really interesting to play. So this is, for example, a little small demo from Ada Rose that she made in A-Frame. Or you can actually use this for interactive visualization techniques. If you add a third dimension to your big data, this means you can create a completely different layer and also change it over time, which means that you will create a different way of understanding for your things. However, this is a JavaScript conference. You all like JavaScript, right? Yeah? That's great, but yeah, I feel a bit awkward because I'm here doing the first talk and I'm actually not really going to talk about JavaScript. So we're going to be talking more about physics and some philosophy, so stay tuned. When I first started out with 3D, I was extremely overwhelmed because if you work with 3D, there's like so many other things you have to consider and you have to work with. I don't know if you're avid players or not, but the thing is, what happens is that you can't just use the same principles that you use in 2D design and development. And when I started, I really wanted to find out what makes 3D, and how do I make great 3D immersive experiences. And the only way for me to truly understand was to actually try and understand how 3D images are rendered. So I would like to talk to you about the physics of light. Because we all live in this world and we all have an understanding of how spatial things work. So we all have the surroundings we are aware of. And it's extremely interesting if you start thinking about this in a different light. So if we talk about light, we have to consider that we have to break down this principle a lot. So what is light, actually? Light is electromagnetic waves of different frequencies that make up the different colors. And from the sun, a lot of different rays are being shot down to the earth. And when they hit an object, the actual texture and surface, like the microscopic surface of this object reflects the ray or make it bounce. And if some of these bounces hit our eyes, we actually can then see. This is very simplified because obviously there's not just one ray that comes out of the sun at a time. So what we actually see is these magnetic waves that in the end hit our eyes. How does this though... So the objects in our rooms and the objects in our environments, they actually define on how we see things. They are interacting with the light, absorbing parts of the frequencies. And so this very selective absorption, reflection, and transmission in the end makes up how we perceive an object. And this is a bit of an extreme detour on what I actually would like to talk about. The point is that understanding these principles helped me be a better 3D and VR developer. There is 3 basic principles of light and object and materiality, and I think we can use it to make better products in general. So one of them is mirror-like objects and surfaces. What happens with the rays of the light is that they actually uniformly get reflected from these glossy surfaces, which means when the rays are all in a really ordered manner, we start seeing the reflection. But there's also diffuse reflection, which means like cloth or other materials that are not mirroring anything. What happens with these rays on the really small surfaces is that they get scattered in random directions. And if then one of these scattered rays hits our eyes, we don't really know, we can't really trace back where it came from, so we don't have a reflection. And then we also have propagated light. For example, glass or milk glass or water, where the rays actually go through the object and parts get reflected. We can see this here in a really nice way, that these 3 principles basically make up all of the materials that we know. So with these 3 parameters, we can kind of already simulate most of the materiality that we have. How does this work, though, if we want to create a digital image of the world? So the first cameras that were developed were pinhole cameras. And you can see that you have a light-sensitive film. I can't move, that's really awkward. Usually I really like to go out of the image and go anywhere. So in the back of this black box, you have a light-sensitive surface, and you have a really tiny pin-sized hole. And basically what happens is that this hole only lets 1 ray per area on the light-sensitive film through, and that ray that comes through will then make the color of that spot. So now I would like to start talking about render engines, which is actually the topic of this talk. So ray tracing is a rendering technique for 3D that has been around for a very long time. Actually, the first ray tracing ideas already come from the 1500s. So this concept has been around for a very long time. And the first 3D rendered ray traced images, they were actually already around before I was born. So I feel kind of intimidated talking about this. But for me, it was really, really interesting to start understanding how we actually do 3D, because most people, for them, it's magic. So as we have seen, these billions and billions of light rays that come from the sun, if they come from the sun and they bounce on an object, they bounce around in the scene and they have to hit our eyes. The problem is that most of these rays we actually never even see, because they bounce around until the energy of the electromagnetic wave is used up. And if it's used up and nobody has seen it with their eyes, it's gone. And if we try to imitate this physical light in 3D space and we would go from the sun to the camera, we would actually lose a lot of computational power. So we actually calculate rays that are never used. So the very smart thing to do is to go backwards, and it's called backwards ray tracing. So we are smart, and we go from the camera through the pixel of our image that we would want to trace. We trace it into the scene, and then we see, is it intersecting with an object in our scene? If yes, we check, is this object actually in light or not? So we create another ray that goes from the point of intersection to the actual sun. This is, of course, a very simplified way of doing this, because right now we don't have any bouncing around in the scene. We actually just check, is this in shadow or not? If the ray is not in shadow, then we just use a background. So in space, for example, that would be black, because there's nothing to see. And this is where the philosophy comes in. If we don't have any objects which reflect the light, is the light even real? So I had a really bad joke this morning when I woke up, because I actually wasn't sleeping well. And I thought, so if there is things that we can only see if they're dependent on other things, maybe unicorns are real and we just don't have a way of perceiving them. I know it's really bad, but still. So I talked about we have to see if our first initial object is in the ray. And then before we checked if there is a direct connection to the light. So what if now there is another object in there, right? Because this object is now actually casting a shadow on our primary object. And it gets more complicated the more actual things we add to this. For example, now, I would really like to point. So here we just have like solid materials. It makes it really easy because we just bounce off. But actually now, if we have one of these glossy or translucent or transmissive materials, from the point of the first intersection, we split up the rays. And that's also what happens in the physical world. Parts of the rays are reflected and parts of the rays are refracted through the object. So you see this here, the refraction rays. So in the end, our final pixel's color is made up by both of these equations that we have to calculate together. So I want you to take a moment and look at this C++ code, because you all love JavaScript. Should be easy to understand. So yeah, who would like to come up here and explain it? Nobody? Oh, that's really a shame. No, I would like to just explain to you what this is. So this is actually a really common thing for computer graphics programmers. It's like a challenge to do, is how to write a ray tracing engine in the least code possible. And the funniest thing is, I did this in Iceland, this talk at JSConf Iceland, and we had somebody do a talk after me, and he actually beat me to it because he added a slide to his deck that showed this entire ray tracing engine in 140 characters. So, yeah. But however, I think this code is not understandable, so let's look at it a little bit more in detail. In the beginning, what we have to do if we want to do ray tracing is to define our objects and how to intersect. So, because we are basically doing a simplification of the whole technique, we're starting with spheres. Because mathematically, spheres are really easy to calculate if a ray hits it or not. So what we need is, we need to have like an intersection method And we want to know the distance of the point from the ray from the camera in order to calculate the next ray. And in our main scene, we have to define our geometries that we want to have and on what locations they are. Because again, if we don't have any objects, how are we going to see the lights? And then we actually just do very simple. We trace for every pixel in the scene, we shoot one ray through the scene and we see what is the final color. Is it in the light or is it not? And to account for these refraction rays and for the colored rays, we actually split up the rays and then calculate them together again with the Fresnel equation. I don't really want to go too deep into this because that's not the point of this talk. I did this because I wanted to understand about 3D. I wanted to understand how this is even done. So this is basically the result of what this simple ray tracing would look like. And the interesting thing is that we have a lot of elements of physical light and physical materiality in here already, which we don't have with other rendering techniques that I will show you later on. So this, for me, already looks kind of good, even though we only have very primitive shapes. But we do have reflection, and it's like physically correct reflections, and we have like color bleeding, so you see this red sphere is actually giving its color to the yellow sphere that's next to it. However, then I hit a point where I was not sure how or if I even wanted to continue. Because now, if we actually want to really take all the aspects into account of the physical lights, we have to consider more difficult geometries, right? Because who has spheres all over the place? It's not like we are in a ball pit or something. So we have to consider that we have multiple light sources. So if you look around you, you will see where all these lights are coming from and how they interact with each other. How are we actually physically accounting for these different materials? How do we define them? And in order to achieve physical correctness, we need to send multiple rays per pixel. Because in the end, the pixel is just a grid, and the grid can have different resolutions. So we want to know, in the middle of my pixel, is that the same color as the corner? In order to account for this calculation errors, we have to send we have to use a lot of samples. And actually now we just bounce if necessary. So bouncing means that the ray actually hits an object, goes to the next object, there it goes to the next object until it would reach the light source naturally. However, we don't want to make all our rays bounce like 1,000 times in the scene until they magically hit one of the light sources. Because then again, we have a lot of problems with computation power. If we don't have enough samples, our image is going to be noisy. And if we have a noisy image, then nobody wants to look at it. That's basically that. If it's just a still image, it's kind of acceptable. But if it's actually an animation or like a game, this is really hard. And I'm saying this because I want to explain to everybody why ray tracing, like real-time ray tracing, is not yet a thing. So what are we actually using for 3D? What are we using for 3D on the web? The most common technique, and it's also one of the fundamental techniques, is rasterization. So basically, we are solving the visibility problem not from the eye to the object, as we do with ray tracing, but actually the other way around. We go from all the objects to the eye. So we take the information from all the objects in the scene, and we use a transformation matrix to make it all flat into 2D space. But that means we lose all the actual information of the objects and how they are connected in physical space. And what does it actually do to our rendering? I mean, I can imagine, but I wonder if you have an idea of what that makes out if we want to actually achieve things like reflection or color bleeding or all these really beautiful things that we saw in the ray tracing example. And I will give you more examples. So then, when we have our flat projection, we map all these fragments, as we call them, to screen space on the actual pixels, and we check which pixels should be colored what. Okay, I will hurry up a bit. So yeah, now we have to map all these triangles that we have to our actual raster image, and you already see the problem. It's a resolution problem. Okay. And we also have a C buffer, which means we can actually layer the objects behind each other, because when we make everything flat, we don't know what's behind and what's in the front. So here you see a very basic comparison between a basic rasterization technique and a basic ray tracing technique. And as you can see, these are all the things that ray tracing can do, which is missing in the rasterization technique. And in order to feel immersed and to feel like this is really a space that could feel like it's real, I think we would go for the ray tracing image, because it's actually based on physicality. This is just a recap. I'm going to skip that, actually. The only thing I want to say is that rasterization has, of course, a lot of support, and rasterization techniques came so far that they can pretend to have all these features like reflection and glossiness. And it's really interesting, because in the new games, there is actually, it's almost not visible that it's not real. Only if you really look closely, you can see that it's all fake, which is nice. So before, we have been writing a ray tracing engine in JavaScript, which probably nobody would ever do, because we don't have hardware acceleration, and it's actually just a really fun thing to do. But if you want to go really deep, then it's going to be hard. So what if you want to do webVR? You're going to check out A-Frame. I have been doing some A-Frame introductions before, but I think that you all really love declarative HTML. So you're gonna be fine doing this on your own. And if you want to try it out, we can do it together. We have 2 days. I'm available for hacking. The cool thing about A-Frame is that you really declaratively just put in your scene that you want to have, and you don't have to take care of rendering. You can actually animate the objects with HTML, but you can also just actually change the attributes of your elements with JavaScript. So I have to do this very quickly. The problem is, if you want to start with 3D, if you don't have content, like actual 3D assets, you can't do webVR. Oh. And this is a really, really big problem, because I can 3D model, so for me it's just a lot of time to actually make this stuff. So everybody loves tables. I made a very scientific table to explain you the problem a little bit. So if I have money and time, then I probably hire a 3D artist. But if I just want to play around with webVR, I'm not going to do that. If I have no time, but I do have money, I will buy my assets on a 3D warehouse, and they're all not going to fit together. If I have no money and time, it's probably the students, I will learn some 3D modeling. And I will take forever to find everything out, but I will have a fun time, because 3D modeling is fun. And if I do have no time and no money, you should probably reconsider your life. But then you can go for curated content. For example, a friend of mine has been writing this really awesome A-Frame plugin, which is also cool about Mozilla's A-Frame, that you could just write your own components, basically, because it's the component entity system, where you can drag and drop 3D objects from Google Poly directly into your scene. It's really, really awesome. So I want to go into this very quickly. Learning 3D modeling. What if I can't do it? I really tried it. Blender is horrible. I hate the interface. Yeah, no, you didn't try it. No, actually, it is hard to get started, but everybody can do it, and I proved it because I did one workshop with my former colleagues at Archeologic. They all managed to model this rubber duck within 2 hours. And I also made it even harder for myself, and I tried to teach Blender to 10 to 13-year-old girls. And they managed. It was hard, but they managed. Maybe I should skip this. Pilar? Yeah, okay. So these are all the things that come afterwards. Like, you have to consider making really nice 3D assets that are actually performing on the web. And if you want to talk about this, please find me later. And to conclude this whole talk, this is an example of what lighting makes in a scene. If we have really good lighting, the whole feeling and the whole immersiveness of the entire scene will get so much better and will actually make people want to reside in your experience. So, to conclude, I could make a lot of talks about this topic, but the takeaways are models, materials, and lights do matter. Ray tracing is extremely cool, but it's nowhere yet near nowhere near ready to be done in real time, unfortunately. And also, artwork is work, so please pay your artists. And I hope that you all are excited about the future, because I am. And I think it's really important that you all know about this new technology, and that you all are interested to at least know how webVR and webAR is going to change the way we work. So please find me with all your questions. Thank you so much, and have a good time.